There are things that you guys still may want to order for either second semester or now. And every one of you guys' things, they have a sheet, and there's also a wish list. And as you guys are going through your days, if there is something that you know you need for a lab or activity you're currently doing, or a lab or activity that you guys are planning on doing second semester, please add that to the wish list, and please make sure when you add it to the wish list, you specify, oops, on the very top. Ooh, hold on. Let me go to a different. Okay, when you guys do a wish list, I need to know the following information. One, the person that is going to be, you're going to get from like the Home Depot, what the item, the vendor, the description, the unit number, like the things that are on the first page. I need to know all that information, as well as the lab that it's going to be used for. So when I meet with your lead curriculum specialist, we could sit down together and be like, all right, this is what people are requesting. This is how much it's going to cost. How can we do this equitably between biology, chemistry, GS1, GS2, and physics? So we have these conversations as a team, so we make sure that we get as much stuff as we can possible through this grant. You guys good? So before they go on, I also have another thing I want to show you. Going back to this, for the observations, people are wondering, what are these observations going to be like? What's going to happen? And I want to kind of clarify with you guys, and hopefully you might want to arrange yourself so you're sitting by your guys' team, sitting by your guys' schools. But the purpose of the classroom observations, and this is straight from the grant literature, it says we're going to be observing curriculum implementation, pedagogical practices. That word's so hard to say, and I said it right. Let's get I can't say it again. And student responses to lessons, and discuss lessons with the teacher. Okay? There are going to be two papers. One paper that we'll print out is going to go to you, and the other paper is going to have it be coded with just your ID number that we have, the last four of your social. No names are ever going to be on it, and that's going to be sent over to the grant evaluator. But those observation forms and how we're going to do the observation forms are on these links. So if you guys went to the PLC meetings, the observation forms look like this. So it's just a simple observation form that goes over the NGSS practices, the 8 of them, and the grant observation focus, and then just a quick narrative of what is going to happen. The procedure that we're going to do for this is there's going to be a pre-meeting session, which will either be done via email, phone, or or a one-on-one conversation. Okay, that should be easy. And the question mainly is, what is your general lesson in a sentence or less? And is there something you want me to focus on, either incorporating phenomena, engineering practices, or incorporating technology? What do you want me to focus on? That will happen sometime before we go in. A day before, a week before. When we go in, we're going to just do a checklist. Did we observe asking questions? Did we observe developing and using models? Did the teacher do it? Did the student do it? And then it's going to be a quick narrative. What is the educator doing? What is the student doing? So we'll do that for 30 minutes to an hour, depending on the schedule. Our goal is about 45 minutes for each observation. And then after that, we will do a debrief. Our goal is to try to do as many people as we can at that school site in a day. So one person could realistically do 3 observations. The follow-up could be a simple checking in for about 5 minutes, or we could schedule lunchtime afterwards with the team. We could do that as well. People have asked, if I want to observe some lessons from somebody else, can I do that? The answer is, if there's a specific lesson you want to see, we will work that out. I just need to have you guys collaborate with me and tell me, this is the day that I want. Can I go to this school site? And we'll have to work out a sub. So I'm not we have some sub money for that. For those of you who really want to check out what other people are doing, you just have to communicate with me. Does that make sense so far? You guys good? So let me show you one more document. And this is something that I will need you guys to hop onto. If you guys go onto the actual Google presentation for the day, there is a choose an observation date with your site team. So I'm going to click on this. There is, let me see if I can reduce the size of this. Nope. So right over here, on this side, this is when the curriculum specialists were available. These are the specific days that we had the ability to come visit your school sites. So far, so good. Right over here are the number of people that were available. So like on October 6th, there were 2 of us available till about 11:30. Then on the 7th, there were 4 of us available till 11:30. So far, so good. Over here are all the different schools that we have, from Benita Vista Middle all the way to Southwest High. The numbers changed slightly, but that was the number. This shows the number of teachers that are on the grant. 4 teachers at Benita Vista High School, 3 teachers at Benita Vista Middle, etc., etc. These right here are not 100% set confirmed dates. I wanted to try to find the schools with multiple teachers. See, like Eastlake High Middle had 4 teachers. So because of that, we're going to need, anytime you have 3 or less, only 1 observer is needed. If you have 4 or more, then we're going to need at least 2 observers. So schools with 3 or more, I really want to just put a tentative date on there. If your school says that date works, leave it be, and I'm going to coordinate with the curriculum specialist to be assigned somebody to work with so we could touch base. I know Eastlake High School, they said we could do October 25th, so I've confirmed that one. So if it's right here confirmed, I'm going to list it down here. Yes, Ed? What if it doesn't work? If it does not work, delete it, pick a different date, and I'll try to confirm it. Make sense? You guys good? You guys happy? So I want to be as collaborative as possible. So as you guys get together with your site teams, look at these dates. If you guys are singletons, or if you just have 3, and you want to choose a date that works for you, just look right over here first. If you could please scan and say, oh, I really want November 1st, but somebody else already has November 1st listed here, then that's probably not going to work because there's only 1 curriculum specialist. So just eyeball it, and I will try to confirm this early on. I know I have Benita Vista High School listed down as October 6th. If this is too ambitious, just let me know, just erase it, and we'll pick a different date. Yes?
Is it this lesson that you're observing?
Good question. So in an ideal world, we would check out one of the lessons that you guys are doing for this grant. Realistically, will we be able to do that for everybody? The answer is no. This is why what we're looking at specifically is how are you incorporating phenomena, how are you incorporating engineering practices, and how are you incorporating technology. Any of those 3 things work. Does that make sense? So October 6th is tentative, really, because I do not know if the other curriculum specialists can do it. But if it will work for you, I'll try to make it work out with them as well, if it would work out. Does that make sense? So please, as you're kind of going through the day before we leave, look at this. As long as you guys have, this is going back to the materials list, as long as you guys have your materials listed of where they're going to go, please take the materials to the places that they go. Anything that is not taken today, I will bring back to my office and I will wait for direction from you with where it needs to go. Make sense? You guys good? And so we're going to have Southwestern College come up. I'm really excited about this next presentation. Then after that we have Leo, you here? Leo. Is Leo here? So Leo will be here later. And then after that we just have a workshop feedback and we're done. You guys good? So Southwestern College, the floor is yours. Oh, Ed. Oh. Okay. So and their presentation, I kind of called it Mythbusters.
Jeff's a myth.
All right, I'm going to try this.
working?
So I'm gonna put that there. Let's see, where can we stick? What is this?
So the microphone.
Is it recording?
It's probably recording. So let's keep it close by.
You guys all read that?
Maybe if we turn the lights off.
Hey, someone picked my day.
I'll go my way.
Yeah.
That's what I was saying earlier. Like I thought it was like. Is there a way to like make it light? That's what I was asking earlier. Is there a way to make the light brighter or something?
You guys good? You should be able to zoom in a little bit more. There's a plus and minus on there. There we go. 6 hours. Hey guys, that's a great question for the timesheets. It's 8 to 3, but with our lunch, so it's 6 hours. All the timesheets are going to be turned in by the sign-in, sign-out sheet. Got it?
I mean, like I could.
Should I start?
You want a microphone?
So,
Get the microphone back there.
can everybody hear me?
Right now.
Would you like a microphone?
Yes. How about now? Can you hear me now?
Would you like a microphone?
Not really.
These things, I don't like microphones.
For the videographer.
All right, I'll take the microphone. Okay, what?
We can't videotape you and hear it without the mic.
Oh, it's for the videotape. Okay, so we were asked to do some sort of misconceptions, and I think I have too many. So I was wondering if you guys read through these things. Does anybody see any that they really want to hear about? Just yell it out, or talk in a group and pick one,
The letter is a little bit too small.
Why don't you just go through that?
Just go through.
or all right. Have you guys all heard that the sky is blue because it reflects the color of the ocean?
Oh yeah.
These are all wrong, right? These are all misconceptions up here. Ocean is blue because it reflects the color of the sky. The Earth's interior is still hot as a result of the heat left over from its formation. Anybody like any of those so far? The third one? Okay, good. That's an easy one. I can do that one in like one sentence. Turns out, well, does anybody know what the greatest source of heat is inside the Earth? Radioactive decay. Exactly. I didn't know it was thorium. Thanks. Yeah. There is still some of the heat left over from the formation, but most of the Earth's heat source is from radioactive materials inside. Just kind of cool. Okay, does anybody ever hear the idea that people say intelligent life is likely in the universe because there are so many planets? It's just got to be out there somewhere. Yeah, like a trick equation. So I think in astronomy, when we think of intelligent life, we're thinking, okay, you might think elephants or your dog or something, but we're like actually thinking about people who build radios and spaceships and things like that. So it's sort of interesting because in that case, we only have one example of intelligent life, right? So if you think about, say, making a graph with data points on it, and you have a sample size of one data point, can you make any trend with that? So can you actually do any probabilistic or statistical analysis at all on one data point? Right, so it always feels like you're being logical when you say, well, it's just probabilistic because there are so many planets, there's got to be intelligent life. But you actually can't make any probabilistic argument with one data point. So there's actually nothing that can be said about likelihood of intelligent life up there. Maybe I should go to the first one. The sky is blue, or do I need to? Do you all know? Yeah. Does anybody know why the sky is blue? Because of scattering? Yeah. Yeah, you could sort of imagine if you could follow all the sun's little photons, particles of light, through space, and they hit the upper atmosphere. Right? So there are all these different colors in the sunlight, of course, and the longer wavelength ones like red tend to pass straight through. They don't bounce off atoms and molecules, but the blue ones do. And so you could imagine following a blue photon bouncing around in the air before it enters your eye. There are trillions of them every second entering your eye from every direction. And so you would say, your brain would say the sky is blue because it receives blue light from all directions, right? But then people always say, of course, well, shouldn't the sky be purple? Or you have a question, Maureen?
Okay, so, and then sunset is red because the blue light gets scattered so much you can't see it, and red is scattered more?
Red is scattered less.
Less.
So you're talking about the sun itself being red, right?
And
So
the sky turns pink.
I kind of want to draw a picture, but it's so easy right now. Yeah, so you can almost imagine, no, I want to draw a picture.
You got your pen?
Yeah.
You want me to move?
Oh my gosh.
Have you moved this over? Have you got a place for your computer?
Yeah. So right, so the idea at sunset is, let's say you're standing here on the earth, right? Here's the atmosphere above you. So there's very little atmosphere that the sun would have to travel through at noon. At sunset, of course, it's over here and you have this long pathway. You can imagine all of the blue getting scattered out of the beam first because it's the shortest wavelength. The green might make it a little further, and even yellow. But the only color that's long enough to make it through the entire distance is red.
So why aren't the horizons always pink?
Like, say at noon, you mean?
Yes.
So at noon, most of the blue photons are scattering in all this entire region around you. And so you're receiving blue photons from all angles, even the part of the atmosphere right near you.
But
So you're getting very little light from over here compared to the amount of light you're getting from around here. Does that make sense?
It's also why the moon's bigger, right?
What's that?
That's why the moon's bigger on the horizon, because magnification.
That's another one. He was just talking about the moon looking bigger when it's on the horizon. Most of that is actually an optical illusion. You ever all notice that the moon looks bigger, right? Try holding out your thumb, the exact distance. And then if you go like that, try to keep the distance from your eyes the same. And 6 hours later, after the moon looks really big on the horizon, measure it again, and you'll see it's exactly the same angular size. If you had buildings and mountains and trees up above you and something that your mind could compare it to, the moon would still look big like that. So, okay. Was there another one? Oh yeah. The ocean isn't blue because of the sky. Obviously, it's still blue on a gray, cloudy day. It's called selective absorption, and water absorbs red. And I don't know, how much time do we have? Should we trade off? Keep going. Is anybody?
You had a question?
Oh, where there was a question? Yeah.
Is there a physical reason or explanation for the mystical green flash?
Yeah, totally. It's mostly refraction, and it requires an inversion layer as well. So, I'll exaggerate the thickness of the atmosphere here to make the thing a little clearer. And so you're standing over here. You're standing over here at sunset, and what a lot of people don't realize is that the sunlight coming in, light bends as it goes to different materials, right? Into water, refraction. And it's a gradual change in the thickness of the atmosphere, and so it refracts gradually. So it's sort of funny, when you think you're seeing the sun up here, the sun's actually already set, right? And so, you know, like a prism will separate colors because different colors refract by different amounts. So it turns out that at the very last instant, the other colors like red and yellow aren't refracting quite enough to bend all the way down into your eyes. They're like going just over your head. And so the last one that you see is green. Technically, you could get a blue flash because that bends even more, but your eye is less sensitive to blue, and the sun puts out less blue than green.
Okay, does it happen every day, or does it only happen in certain?
So it requires a steady, non-turbulent atmosphere. It doesn't have to be still, it can be windy, but as long as the wind is steady and you don't have turbulence, you can get it. But if it's turbulent, then this sort of really subtle effect here isn't going to work.
So does the green flash only last like a tenth of a second or something? Or
Something like that. It would probably depend on the lack of turbulence in the air. If it's really steady, you might get, I don't know, half a second. I'm not sure what the longest one is, but it's really short.
Have you seen it?
I have. A couple of times just from on top of Coles Mountain, and I think a lot of people tend to see it at the beach. How many of you have seen the green flash? Not many. Okay.
If you're colorblind, you're gonna have a hard time too.
I guess it's so there's an informal homework assignment. Go to the beach on a nice day and watch the green flash or something like that. All right. Anybody like any of these three? Or I can just yeah, question.
What's the argument now that black holes don't even exist?
Haven't heard it. Are you talking about information theory?
No, black holes.
Yeah, well,
Are they
information.
proven to exist now versus being more of a theory?
Oh, did you say proven not to exist or
Yeah.
proven to exist?
Proven not to exist.
Yeah, I don't know about that.
All right.
Because it seems like there's so much observational evidence that suggests they're there and out there. So I don't know about, was this just like yesterday or?
No, it was a couple years ago.
Yeah, not familiar with it. Yeah, actually, yeah, Google it, let me know. Because there's two really strong angles on the evidence for why we think black holes exist. Maureen?
Do galaxies recede faster than light?
So you're looking at this one, yeah? You're thinking, wait, doesn't that violate special relativity? How does it move faster than light?
Yeah.
So, okay. It's odd at this point in cosmology. The most instructive thing is raisin bread, okay? So I'm going to draw you a picture of raisin bread. Hold on a second. Okay, here's your raisin bread before it goes into the oven, and we're just going to look at 4 raisins across the bottom, and we'll number them, let's say. And then let's say you bake it for 1 hour, and it's special raisin bread. It gets really big, and your 4 raisins. Your 4 raisins haven't actually moved through the bread, right? What's happened is the bread has expanded. So Einstein's special theory of relativity would be addressing an issue of a raisin moving through the bread or a galaxy moving through space. But the expansion of the universe isn't galaxies moving through space. It's the space itself expanding, but the galaxy staying relatively stationary. And you can see Hubble's law in here. Like, let's say they're 2 inches apart up here and 8 inches apart down here, right? So 1 and 2 have moved at a speed of 6 inches per hour, right? Because they went from 2 to 8 in 1 hour. But 1 and 3 have gone from 4 to 16 and they moved twice as fast, right? So does that make sense? If you look at raisins 1 and 3, they started out 4 inches apart. They ended up, if they're all 8 inches apart, 16. So they went from 4 inches to 16. So 12 inches per hour instead of 6. So the rate at which the universe expands depends on how much of the universe you're talking about. So all you need to do is talk about a big enough chunk of the universe, and you'll have 2 raisins or 2 superclusters of galaxies moving away from each other faster than the speed of light. But because they're not moving through the space, it doesn't violate the special theory of relativity. So,
Thank you.
Really?
Kids.
Draw dots on a balloon. Yeah, and you can do a wavy line to show cosmological redshift. Yeah. So yeah, you can get light emitted from a galaxy moving away from us faster than the speed of light. So first of all, yeah, you can have those galaxies. But there's this thing called the Hubble distance, which is the distance from us at which galaxies are all receding at the speed of light, like I was just talking about with the raisin bread. Right? Anything beyond that is moving away from us faster than the speed of light. But if you think about, if you try to imagine a galaxy just a little bit beyond the Hubble distance, and it's emitting light toward us, but it's sort of like the river is going really fast this way and you're paddling upriver, but you're not getting anywhere because the river's going downhill faster than you're paddling up, right? So you're paddling up relative to the water, but you're actually still moving downhill. Okay. But the distance at which the objects are receding at the speed of light, the Hubble distance, is actually getting bigger. And so you can imagine, even though the galaxy is moving away faster than the speed of light, it sends off little photons towards, let's say you're the Earth and I'm this galaxy far away, towards you. But the photons are actually getting further away, but the distance at which the recession speed is the speed of light is getting bigger, and so eventually the photons catch that line. And then once they get inside that line, they start moving towards you. Yeah, it's sort of strange, right? The universe is a weird place and difficult to picture. Maybe that's not a very good one. I didn't do that. So the last one, the radius of the universe is approximately 13.8 billion light years. Yeah, it's actually, well, the radius is somewhere around 42 or 43, and yeah, you got 85 for the diameter. So the idea is that this is approximately the distance in light years to the Hubble distance, right? But there are galaxies that we receive light from today that were on the order of 10 billion light years away, or something like that, when they gave off that light. But in the intervening 10 billion years for that light to get to us, the universe has continued to expand, and so those things are now much further away than they were when the light left them all those years ago. So it's one of the fun things about cosmology is you always want to keep in mind here and now, there and now, here and then, and there and then, because light travel time is always so important for everything you think about. Yeah, it's totally like a mind blow, right? Then, of course, on top of it all, the whole thing is bent, the space is curved, and so on. The black holes, yeah, so this is always funny. My students are always talking about black holes sucking everything. I mean, suction implies partial pressure, right? And this is a vacuum, there is no partial pressure. Pull is the better word, because you're dealing with gravity. But it's always a fun question. If the sun were to become a black hole, and of course, it never will, right? It doesn't have enough mass to overcome something called the Chandrasekhar limit. So, but imagine, like, what does your intuition tell you? If the sun suddenly became a black hole, what would happen to the Earth? Would it get pulled in?
Our year would get real short.
No. Yeah, so it actually, nothing would happen. Well, we would get cold, but the orbit wouldn't actually change. Because if you think even just in terms of Newton's law of gravity, has the mass of the sun changed when it becomes a black hole?
Well, it depends. Is the black hole the size of the sun, or is the black hole the mass of the sun? There's a really good video by Chris.
Yeah, so the black hole, even the event horizon for a mass the size of the sun is way smaller than the sun, right? But the distance between the center of the sun and the Earth hasn't changed. And the mass of the sun hasn't changed when it collapses. And the mass of the Earth hasn't changed. So none of the three quantities in Newton's law of gravity have changed, right? The masses are the same, the distance is the same, which means the orbit can't be affected. You're frowning, like you don't like that. Should I say more or less? Yeah.
But does the density modify the gravitational pull?
No.
The density.
No, it does. Well, yes and no. So here's the thing about black holes. Their strength is not in their mass, it's in their small size. Right? So if you imagine originally, let's say the sun is that big. And so considering how close you can get to the sum of its mass, if you could stand on the surface of the sun, you would still be on the order of 500,000 miles away. If that mass collapses to become a black hole, its size is now smaller than the little point I've just drawn, which means you can get literally millions of times closer to the entire bit of mass. So it's not that the mass has changed, but changing the density allows you to get closer to it, and therefore the distance in the denominator of Newton's law is smaller, and so the force becomes so much larger. Does that make any sense? Maybe. Sometimes I just talk and things. So another interesting, I don't know, do you guys even know what a black hole is? No. So classically speaking, you think of a collapsed star that's gotten down to zero size, right? Because the smaller it gets, the faster it gets smaller. But since around 1915, with Einstein's general theory of relativity, you now have to deal with the fact that the rate at which time passes is changing, right? So the singularity probably never forms because time actually stops before it gets to that size, zero size. But it's sort of crazy because if you were to go inside an event horizon, the reason, so classically the reason light can't get away from a black hole, and that's why it's black, the reason light can't get away is because the escape speed, like on the Earth, how fast you need a rocket to go to escape the Earth's gravity. The escape speed from a black hole is greater than the speed of light, so nothing can get out, including light. But the more modern view is what's really going on. You could sort of imagine if you're inside an event horizon, and think of all the different directions that you could point, up, down, behind you, everywhere. Turns out every single direction you're pointing is actually pointing towards the middle at the singularity because the space itself is bent, right? So you could turn on a flashlight and shine it in any direction, and every single direction would end up back at the singularity. So that's another, I think, a better way of understanding why you can't get out, because there is literally no path outward.
So is that where you lead to like talk of wormholes and things like that?
So wormholes don't exist.
Okay.
Yeah, that's one I should. I'm sorry to break the news to all of you.
But Star Trek.
Yes. Wormholes, wow. I didn't know that was going to be such a big So yeah, sorry to break the news. Also, Pluto's not a planet. Yeah, you're all good at that. So wormholes, yeah, don't exist. It's called an Einstein-Rosen bridge, and it's a nice little mathematical trick in the Einstein's field equations for general relativity, but it's not a realistic thing. Okay. Sorry about that. But another crazy thing to think about with black holes is, this is going to sound a little bit weird, but the properties of time and space are actually reversed inside the event horizon. So, like I could, you know, if I want to get to the other side of that chair, I can just walk around the chair, right? But if we think about properties of time, it's 128. I am not going to be able to get to 135 without going through 130. Does that make sense? I can't walk around 130. But inside the event horizon, those properties are reversed. So you can walk around time, so to speak, but you can't walk around the singularity. So the reason everything has to go inward into the black hole is because that location at the center of the black hole is as inevitable for somebody inside the event horizon as 130 is for all of us in this room right now. It's that you can't go around it. Anyway, what else? I think that's about it. Hopefully, did I like blow your mind a little bit? I hope. Okay. Cool. Who's next?
think my things are so mind-blowing or whatever. So I deal in biology, so we don't really have like probably big misconceptions, and they're probably not, my things I don't know are necessarily misconceptions that you guys might have, but more what I've noticed, misconceptions that my students ultimately get that sometimes make it hard for them to learn some of the concepts they have to learn. And for me, a lot of them are either we've just been told wrong, like the first one, artery versus vein. So at some point along our education, I don't know who does it to us, but the urban knowledge is that arteries are called arteries because or why are they called arteries, or why do we draw them red on a diagram? You know, why do we make veins blue? So yeah, that's usually the answer, oxygenated versus deoxygenated. At some point along the line, someone told us in school probably, or parent, I don't know, and they said, oh, the reason the arteries on that map are red is because they have oxygen, and the reason the veins are blue is because they don't have oxygen, and that's why we label them, and veins look blue, so we call them blue, right? And so, anyways, that's actually not why. So, arteries are red and veins are blue, but they're not telling us about oxygen at all. And actually the name and the color are telling us something else, which is what direction the blood is flowing in. So red labeled things will always be taking blood away from the heart, and blue ones will always be bringing blood towards the heart. Right? So red goes towards the heart and blue goes away from the heart. The problem with that is, sure, a lot of the time the blood returning to the heart does have less oxygen, right? And a lot of the time the ones going the other, oh, I did do that backwards. Look at that.
But you know what, Sharon? I noticed, but when they do the pulmonary artery, they do change the color for that.
Sometimes on some modern models, they'll go to a third color. They'll make it purple.
Yeah, okay, because, purple, it says
Yeah, actually, I didn't notice I did that. Let's see. Of course I did. Yeah, arteries go away. And the red go towards. Sorry, I didn't mean to do that backwards. Blue. Blue are going towards, red are going away. Whatever I said, that now is red. Right? And here's the thing, because there are exceptions. So if they learn that, they're going to get it in their head. And then eventually they learn the pathway and everything, but then they still keep missing questions about oxygen because that's actually is incorrect, right? So we have the pulmonary vein, which is the most oxygenated blood in the body. And it's a vein. Right? We have the pulmonary artery, which is the most deoxygenated one. And we also have umbilical veins and umbilical arteries. Umbilical veins are also high in oxygen, and arteries are also low. Right? So it's just telling direction, and that's all. With arteries going away, I said it correctly, and veins going towards. Right? And that's it. And it just, again, they'll memorize their things, but at some point they have this little hiccup in the back of their minds that make it hard for them to think about oxygen levels. Let me see what else did I have. Oh, air. So air is another one that, air and water are things that my students end up with a lot of misconceptions for. They don't really understand. They understand, they've taken classes, they know that's made out of molecules, they can see it move in the wind, but they still don't really believe that it is something. And they don't understand how it has pressure and mass, and how air can displace water. Right, so then, let me do a thing here. Right, we do this experiment in biology where we take this aquarium Elathea and we put it in sunlight, and it's an aquarium plant, so an aquatic plant, so it lives down in the water. Right, and as it begins to photosynthesize, the oxygen bubbles begin to form off of the plant, and then they rise up. And we capture that in a little something like this, right? So you got the Elathea plant, you're shining a light on it, it's making oxygen bubbles that are rising up. And this whole tube is filled with water. So I drew one that was different. Right, so we start off at time 0 and we clamp it, then we put a light on it. And as the light goes, the oxygen bubbles bubble up, right? And it used to be at time 0, it was filled all the way to the top with water. But we've got a clamp on there so the air can't escape. Right, so eventually, the water bubbles go up, and we know that the air bubbles go up, and we know the water gets displaced, and eventually we have like a gap of water a gap of air that we can now measure, and we can see how much oxygen it produced in a given time. Well, my students struggle with this. They can see the oxygen going up because because they don't understand that oxygen, the gas of air has a force, right? They can't understand where the water went. Right? Because they can't follow it. So they think that where the water go, it must have gone into the plant. So therefore it's disappeared. They don't understand it's the actual. And I was preparing for today's program, and I went back trying to look in time, and I found these. I was Googling on the internet and trying to find the history of some of. I've been curious about the history of engineering and science in the curriculum. I found this old lab book, actually. It's a K through 8, believe it or not, design lab book, and it was called something like Science on a Shoestring or something. But it was interesting because they had a series of labs where they were working with kids where they were trying to understand the concepts of air. And one of the things, they gave them like a container, and they said, okay, if I take the cup and I put it straight down, what'll happen? You know, what's in the cup? And just getting them thinking about it. And I was like thinking, my gosh, you could do a bunch of engineering design with this. And then after they had done that, they said, well, what if I take and I put a crumpled piece of paper into the plastic cup, the same cup, and assume that you can keep the paper up there. If not, you know, put a little tape on it to hold it. And what happens when I put that straight down in the tank? You know, will the paper get wet? Will it not get wet? Why not? And the idea that there's a force, and if they do it correctly, it won't get wet, right? But then you can ask, but what happens if I, you know, put it down at an angle? You know, and obviously, eventually, it gets wet. Right, and again, this little guy, it's just this idea that air and water don't occupy the same space. I like this little demonstration because you take and you fill this cup with water, and you put it straight down filled with water. This one's filled with air. And you put it down and tilt it so that the air bubbles go up and then displace the water back out, right? So they can see that that's happening. But I spend a lot of time in the 101 lab. They understand the photosynthesis. They understand oxygen is being made. They can describe the equation, but the lab setup is confusing them because they can't understand where the water went. So I don't know, maybe some of you, I don't think by the time we get through the science curriculum, we probably have that concept down. But I was thinking, in physical science, is that addressed in the core?
Gas law.
Gas law specifically.
Yeah, that's not
Right, but it's like they get so mystified with that. And I'll be trying to explain the physical science, and I'm not so good at that. That's not my area. You know? And the last one was, this is a cultural concept. When I start teaching osmosis, when I start teaching movement of things diffusing through capillaries and whatnot, they have to understand a concept about concentrations, concentration gradients. But there's a cultural problem that I've discovered that impairs people of Western thinking from understanding dilution or the power there. And this is it. It's the way we communicate. We take water. I've got concentrated orange juice. I pour the water in there. I diluted the orange juice. I don't have enough milk to serve my family this morning. I'm going to pour a bunch of water in there and shake it, and I'll have some dilute milk. And we always talk about what water is diluting. But we never talk, culturally, that the stuff simultaneously is going back and diluting the water, and that ends up giving them a hang up when they try to understand, well, where'd the water go? You know, like you do a simple experiment where you say, oh, we take the concentrated water, concentrated orange juice, we add the water, we mix them together. I had pure OJ at 100%. It went from 100% down to 10%, so we know that the orange juice has been diluted. Right? But there it is, it went from 100% down to 10%. But simultaneously, what happened to the water? It's no longer at 100% pure, maybe it dropped to 90%, so it was diluted by the stuff. But then they'll just be hung up, well, where'd the water go? If there's less of it, now it's at 90%, where did it go? And they're totally okay with it. The OJ didn't disappear, and that it was diluted. And some of you that teach osmosis, you probably ran into that, like, and you're like, how do I dispel that? Have you guys found any good ways of dispelling that thinking? It's a very rigid, but I think it's cultural.
I kind of get down to percentages and talk about like 100% is 100%, you know, so if there's 60 of something, there's got to be 40, and the reverse, the inverse has to be true. Right. But they don't almost get it.
Yeah, so it is a cultural thing. So at any point in time, we can be talking about the fact that when one thing dilutes something, then the other stuff simultaneously went back and diluted it. Right. And that's what I was sort of showing here, that simultaneously they're both diluting each other. And my last one that I wanted to talk about with you guys, and I was going to say the reason it's so important for me is they have to learn about osmosis, they have to learn about the kidneys, they have to learn about gas exchanges, and as things are mixing and changing percentages. My last one is I discovered when I was teaching, to teach biology, I always have to teach some chemistry. And I was going over ionic bonding. And we created sodium atoms and we had created chlorine atoms and they had them on their desks. And I was asking, why are they so common? Why do those two atoms find each other? And I always say, why do we have big salt mines filled with salt? And I'm trying to get them to talk about the orbitals and why they're combining. And this particular day, I got silence out of my group. This was almost 20 years ago. And finally, I said, well, why is there more salt in the ocean? I was just trying to get them to think, like, why do these two atoms finding each other? And I did not get the response I expected. Some of you have probably had this response. So, well, why is there salt in the ocean? And a hand went up. And they said, well, because of whale sperm. And I went, what? So, oh, yeah, that's why the oceans are saltier than the lakes and rivers. And I'm like, no. There's a water cycle that you guys are trying, and I'm like, wow. So when I came here, actually, in June, when you guys started saying, we're going to have a theme of water, I'm like, oh, thank God. Right? Because maybe there'll be some that get the water cycle and the replenishment, and then they'll say, okay, I'll explain it to them. Okay, then they agree that the salt came from the rocks and went down the rivers into the ocean, but then they'll say, but then why aren't the rivers the same saltiness as the ocean if they're carrying all the salt there? Right? They'll still get hung up on the salt sink in the ocean and it's not being necessarily replenished by springs and fresh water and snow melt and all these other things. Right? So I actually, in preparation for this, I went online and it is... Okay, so when I started teaching 20 years ago, it was just urban legend. Now there's full internet sites, full internet hoax. There's sites that dispel the hoax. There's sites that actually tell the hoax. And they're really detailed with they're very detailed sounding, right? So they'll say, a whale ejects 400 gallons of sperm per ejaculate, and only 5 gallons makes it to their mate. I looked it up. Okay, a whale would die if it ejaculated 400 gallons of sperm. Right? So, but the thing is, it's so detailed, they have a hard time distinguishing between these facts that seem very factual and like what they're learning in science, and it just seems more plausible to them that it's the whales than normal water cycles. And have any of you, I started polling my classes now. At least half of my students every semester believe at the start of the semester that it's whale sperm. That's how prevalent. And they'll get these hoaxes that come through their Facebook sites. There's full-on memes. Oh my God, my mother said don't drink the water because there's sperm from whales in there. And there's like full hoaxes that they get. So at the same time that you're trying to teach them science. So has anybody found this in their students?
I have, because I try to do a lot of this stuff, and I have them read science articles and write summaries of real science articles from a list of websites. And one of them that I got was a student who said that global warming was going to cause zombies. And he picked that article because he doesn't believe in zombies. And it was because that was the hook that they used to get them to read the article. And the article was about old viruses and bacteria that might come undissolved from the ice.
From global warming.
From global warming. But that was the hook for the article. So that was what he went away with, the misconception that there was a science article out there that was...
I tell you, if you survey your students, you'll find they have this misconception. Now, I didn't hear that when I was growing up. And I've talked to people and they said, yeah, I heard that in 5th grade. That's where it comes up. It's like they're talking amongst each other. Maybe they're pre-puberty and they're starting to think about these things. And it, so anyways, that's all I have to say.
So happy to be following sperm. I can't follow sperm. So first of all, I have to preface this all by saying that the misconceptions that we have, we're not like insulting any of you. This is just things that we get from our students, and we assume that maybe you guys get similar things from your students as well. And so we're just trying to demonstrate how we handle them to a certain extent. So some of the questions I get in geography, and there's a lot of them, but the first one I'll look at is seasons. So why do we have seasons? And by the way, before we talk about the seasons, of course, we talk about Earth's orbit around the sun, and we know that there's a perihelion and an aphelion, where aphelion is when we're furthest away from the sun, and perihelion is when we're closest. And then I make a mnemonic for my students to remember what aphelion is and perihelion, where I say aphelion is far, and there's a big A sound in it, so aphelion, so you'll never forget now. Like, you'll walk out here going, oh, this is bullshit, but then when you walk out, you go, oh, he's right, aphelion is far. So that's the first thing we talk about, perihelion and aphelion. And then we discuss, okay, so why do we have seasons? And then we'll talk about the tilt of the Earth as well. But then the answer always goes back to aphelion and perihelion. But then the problem is, aphelion, when we're furthest away from the sun, doesn't occur in northern hemisphere winter, it occurs in northern hemisphere summer. And then perihelion's the opposite. So then they get really, really confused. And so we talk about tilt of the Earth, 23.5 degrees, and then the Earth revolves around the sun, and so you'll have summertime in the northern hemisphere, and this is wintertime in the southern hemisphere. So solar rays are a bit more direct, and then you get longer daylight hours, right? And then here is spring or fall, and here's winter for us in the northern hemisphere, and summer in the southern hemisphere. So then I continue that conversation. I go, okay, well, what if we had a 90-degree tilt now? So here, the North Pole is pointing toward the sun. And then I just stop and I go, how many seasons are we going to get? So I will ask you guys, how many seasons do we get if we have a 90-degree tilt and not a 23.5-degree tilt?
2.
1.
Okay, well, what is this season right here in the northern hemisphere? Summer. It's just really extreme because it's 24 hours of daylight, and you don't want to be on the North Pole. But now what's this season? What comes after summer? Fall. And now what do we have? Winter. It's just really extreme. And then what do we have? Spring. And then we go back to summer. So it doesn't matter if it's 23.5 degree tilt, 1 degree tilt, 89 degree tilt, 90 degree tilt. If you have tilt, then you will have 4 seasons. But then I extend the question and I say, okay, well, get rid of tilt altogether. 0 degree tilt. How many seasons do you have? 1. Well, now you could have 1, but now, okay, well, let's talk about perihelion and aphelion. Does that make much of a difference? So now we're going around, and you would think that you would just have 1 like constant spring-fall type season, but there will be a slight difference. At least some students will argue this. They'll say, well, during perihelion, when we're closest, shouldn't we be a bit warmer? And when we're at aphelion, when we're furthest, shouldn't we be a bit cooler? And it's just sort of a cool topic to think about because now students are really trying to put 3-dimensionality into perspective. And when I draw pictures, like I'll draw it with a certain perspective. Like here's Earth, and we're standing here looking in. But sometimes I'll draw the picture over here, right? So we're still looking this way. The season's the same. We're just looking at it at a different perspective because all these textbooks will have like Earth here or here, and it never flips. And so students always think, well, summer times mean that we're over here in the west. Like there's no west. We're revolving around the Earth. So that's one misconception. That's, for me, a lot of fun. We spend a ton of time with it. Another misconception is we talk a lot about electromagnetic spectrum. So we'll go a lot through visible, and the stuff that Jeff talked about was sunrise, sunset, daylight being blue, red, pinks, all the colors is really cool. So we go over Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And we talk about gamma rays and radio waves, and we talk about energy and all this stuff, energy of photons. And so that we know energy is related to 1 divided by wavelength. So we know that gamma rays are extremely high energy, and we know that radio waves aren't as much because the wavelengths are different. And then I'll talk about colors, and I'll say, okay, you got Roy G. Biv. Which color is warmer, more energetic, red or blue? The answer is always red. Like I'll always get red. But of course, when we talk about physics, blue is actually the warmer color because blue has the shorter wavelength photon, so it's more energetic. And then the question always becomes, well, if you're a ironsmith and you're hitting that iron, it's like red. And of course the answer is it's red because it hasn't gotten hot enough to emit the blue photons. So then we talk about, well, why is it this constant perspective that blue is cold and red is hot? So that's one of the reasons. But then the other is people talk about ice in the Antarctic because they've seen pictures of blue ice. So then we get to talk about how there's a certain refraction in ice that lends itself to see a lot of blue. But then what's really cool too is oftentimes if the day is just right, you can see really cool blue shadows, like in the Antarctic. And the question is, why can you see blue shadows? So here's the scenario. You're in the Antarctic ice sheet. It's daytime, 24 hours. The sun is up. Beautiful blue sky. There's nothing else except you and your shadow. And if the shadow is a tinted blue, why? Yeah.
Because the sky is blue and it's backlit with all the blue light.
Yeah, that's exactly it. The sky is so blue. Raleigh scattering is pretty intense. Like, I remember the first time I was a bit younger, like, younger's relative, I was still an adult. But I went with my wife to Kauai, got off the plane, the green from the grass and the blue from the sky, like, actually really hurt my eyes. I wasn't ready for it, that distinctly deep blue and green, and so it hurt. Well, imagine if you're in a situation where you don't have a bunch of pollutants in the sky, don't have the big particles to have a bunch of me scattering, and instead all you got is like Raleigh scattering, then you're gonna have a nice blue coming from the sky, a nice blue glow. So if you get rid of the only other source of light, which is the sun, and you're left with the blue sky, then you're gonna have a nice blue tinted shadow. So we talk about that in the class as well. Another big one that I get a lot of is when we do Coriolis effect. And then I get a lot of students quoting The Simpsons. When The Simpsons went to Australia and Bart flushed the toilet and it went in the opposite direction. And so the question becomes, is that going to happen? If you go to Australia and you flush the toilet, will it spin in the opposite direction because of the Coriolis effect?
If your toilet is 500 miles across, it will.
Maybe. So, you guys actually don't know the answer, or? Well, you all know that, okay, the Coriolis effect is like a really weak effect. And like it's affecting me right now when I'm walking. It's affecting all of you when you're walking. But it's a weak effect. And so the force that I walk with is stronger than the Coriolis. If you go bowling and you keep slicing it, you can't blame Coriolis because you suck. It's just, you suck. And then the same is true with golf. Like if you keep slicing the ball, it's like because you suck. The angle that you're hitting the ball with and the air friction, that's all much, much stronger than Coriolis. So as Jeff said, if your toilet bowl is like 500 miles in diameter, then you might see a Coriolis effect under the assumption that you have a neutral drop mechanism. So like the water is coming straight down and it's not coming at an angle, which is what a lot of the toilet bowl manufacturers make their toilets. You flush the water and it comes out at a certain angle and it spins. So it's an incredibly weak force, or I should say weak effect. And so it's not going to happen unless, like Jeff said, you've got a big bottom with a big toilet, or you have like the drop mechanism is neutral.
Isn't it sort of perspective too? Let's you're on this side, and so you flush and it's going this way, and you're on the opposite side of the earth, so they're both flushing to the right, but they'd be spinning oppositely based on perspective. This one's going to the right, this one's going to the right, but they're going in opposite directions.
I don't think so.
If you're viewing it from up here.
If you view
I know what you're saying.
Okay,
I know what you're
saying. I'm not saying that actually.
Like if the Earth was transparent, and you're looking at a toilet flushing in Australia from here.
Just perspective. Just perspective. I'm not saying they're going different ways.
Right. Yeah. You're stumping me.
I'm just wondering if in Australia you do it the other way, like driving on the left side of the road versus the right side of the road.
Maybe they have their jets on their toilet.
Yeah, I mean. See, I think there's two questions. Does it go the other direction, and is it because of the Coriolis effect? It could go in the other direction, yes.
Yes, it could go in the other direction, but not because of
Not
the
because of the
Coriolis
effect, yeah.
Correct.
So
It would be the shape of the toilet bowl or
the
what's
dynamics
in
or
it.
the technology, the way, or yeah, or if it's one of those ones that goes straight down.
I got one more that I need to give it to David. One more. Why do you cool off when you sweat?
Sweat evaporates.
Right. So students always think that when you sweat, all of a sudden there's cool water on you from your body. Cool enough. But of course, that's not true. When you sweat, the water droplets form on your skin, and then heat from the surrounding air and even your body goes into the water. That evaporates the water. The water then in vapor form goes away, and it takes the heat with it, right? So that's why you cool when you sweat. We get a lot of really cool questions about that, and those extend to if you're bald or not bald, why you stink or why you don't stink, which is a completely different topic that we won't get into
That's
now.
a microbiome question.
Yeah. All right, I'm going to leave it at that, and I'm going to give this over to David.
Well, this is a pretty tough fact to follow. I must say that my examples are a lot more mundane. As a chemist, we spend a lot of time in the lab, and for many students, this is kind of the first in-depth kind of experience doing experiments and making observations. So everybody remembers sig figs, right? The issues with sig figs. So that is probably one of the biggest issues that students struggle with. So everybody remembers our titrations, right? You have the burette, and it's marked in milliliters, 0, 1, 2, 3, down to 50. Well, this is an issue in and of itself because they have real problems reading from 0 to 50. So for instance, if the meniscus is here, or over here, they'll read it as 2.1 instead of 1.9 going backwards. So trying to kind of get them to dial into what their instrument is and how it reads it. The other thing is that our burettes will have 10 markings in between the milliliters. So I'll often see them recording to 1.0 or 1.5 instead of to here. But then when they do their calculations, they'll have, because the calculator will subtract and divide, they'll get 5 or 6 decimal places. So I always have a real struggle trying to drill that into their heads. And I'm sure my fellow chemists, you have the same issue, right? And yeah.
We try.
Yeah, same
Not just
here.
chemists, physicists too, we try.
Biologists, we also.
The other kind of very practical aha moment for our students that I see almost every semester is there'll be an experiment, let's say, where they're making some cereal dilutions. So they have to pipette a total of 5 mils into each of one test tube. And what they'll find is that some test tubes will have meniscuses that are at different heights. And they always freak out, saying, oh my goodness, the pipette's broken or something's wrong. And so then I go, okay, look at the test tube, look at the glass. Is it thinner or thicker? Is the test tube taller or shorter, fatter? And then like, oh, okay, right? I always run into that every semester. Let's see, what else do I have? The markings on the glassware. Our students are very trusting. So if they see a beaker that says 100 mils and 50 mils, they think that that's extremely accurate, right? And then I say, okay, let's use a graduated cylinder, right, or a burette and dispense it in there. And you'll find that depending upon which glassware you use, you have different degrees of accuracy and precision on that. So again, this is kind of a common thing I see again and again. Yes?
Back to the burette, I was reading somewhere in the AP in the college board, when it comes to approximating that second digit, is there a rule as to what you set that value as?
Just be consistent. Well, what did you read?
I'm trying to remember, but there was a rule for like how close as far as like either do 0 or 5.
Yeah, or 3.
It was similar to like when you rounding for 6 figs, but it was, I don't remember what it was.
Yeah, if it's even, if it's like an even number and then you round up or round down.
Something like that, but for determining what that value should be. So I was just talking just approximate 1.5 what?
Yes.
Have two people look at it and agree. But I read somewhere that there's actually a procedure for that, and I wasn't familiar with it.
I'm sure there is. I'm not familiar with that either. What I tell them is try to be consistent. So if you see it, you know, close to the line, make it 1/3, and just always make it 1/3. Or if it's halfway, or you know, 0.7, 0.3, 0.5. But again, that really kind of harps into the uncertainty in the measurements, and that's another kind of global misconception, is that a lot of students, when they take science, they think it's very black and white, that if you make this measurement, you make this observation, it's the absolute truth. And so I spend a lot of time with statistics and probability, and if you do the experiment multiple times, you can have a range of values, a range of results, and that's a very hard concept for the students to come in. And I think the last one I'll leave on kind of a philosophical note, following my colleagues, was how many people have heard that all motion stops at absolute 0 Kelvin? Right? Is that true?
We don't.
No. That's not true. That's again a common misconception. At absolute 0, everything is in its ground state. You have a perfect crystal. So there's always going to be some lattice of molecules, let's say if you have a perfect crystal, and they're going to be vibrating in 3 dimensions. And every one will be vibrating in exactly the same lowest quantum state. All the quantum numbers for the vibrations will be exactly the same, so it'll be 0 entropy. However, has absolute 0 ever been obtained? No. It's, as far as we know, although some people have claimed there's negative entropy, negative Kelvin, but those are I'm kind of skeptical on that. Yeah. Yeah. So anyway, so I think that's where I'm going to leave at. But a lot of hand-holding when we're doing the experiments. A lot of students don't trust their own observations. They see something surprising, or they make a measurement and they think immediately that they did it wrong. And I have to encourage them to say, yes, you made that observation. Now work it through and kind of work through that. And I think that's it.
Are we up, Antonio?
We have about 10, 13 more minutes till we have to go on to the next thing. So you have a few more.
Well, we just, when we were putting this together, we were just coming up with a list of items that we see a lot of in our classrooms, which are sort of fun and frustrating at the same time. We wanted to leave a few minutes at the end if any of you had anything that you wanted to share. And there's no pressure, like you don't have to have anything. But if you have if you have anything that you all want to share that you get a lot of in your class, please feel free.
I have one that went to when you were showing this. I actually looked it up, but when you were showing the whale sperm, because I don't know about the rest of the people here, but my kids like to argue science using Disney movies. YouTube is.
So there's a Disney movie about that?
No, but they'll be like,
well,
like we talk, like I tell them about the Lion King and how Simba and Nala must be brother and sister because only one male lion reproduces with the females in a pride, and they're like, what? Like what? They get really grossed out. It's awesome to watch their faces. Or like with hyenas, they complain there's no food, but they're surrounded by bones, and hyenas can digest bones, so there's plenty of food. But anyway, they the other one though that they all try to tell me is true, and so I show them online. I had to plug this one in. How do we? This is a great website. If you guys know about the flying spaghetti monster?
Yeah.
Okay. So this is kind of on a similar vein. Yeah, it's a map.
I'm not sure if you have it out. We
I
can
don't
probably
have-
pull it up on here.
I don't have my little. Yeah, we just look it up in there. It's just just put in say the Pacific octopus, Pacific Northwest octopus, or a boreal octopus.
Oh, I got the other one.
Yeah, I have to do it's a lightning drive. Just put in a boreal.
I gotta find his browser. Here, I guess. No, we gotta fix this. Yeah. But I don't know, why isn't it predicting what's on?
Well, I think I should plug that in.
It's showing us the screen, it's just not showing us what's on the screen.
All right, so.
Yeah, you got it.
So this is a
Technical
website
degrees for everyone.
You can bring this up. I like Octopi. We talked about this some of us at the last biology meeting we had. And this is an example I show my kids, and I talk about this, and they get all excited about. We need to save this Northwest Pacific tree octopus because it's being, endangered. And you can even get everything from, there's this name. It's got the genus and species. They've got pictures. They've got historical anecdotes where, here's the range with the spawning waters where it lives. All the way down to the Cascadia Evening Post with a picture of 1923 with a lady wearing an octopus hat. This is another reason why they were going towards extinction. So you can give them all this stuff, and they're kind of get really they believe it, and then you kind of tell them it's all false and watch them cry. You can show your support. You can actually buy T-shirts and stuff that say this stuff. There's been sightings. You put it on sightings. Here was one. I hiked up Mount Baker, and they have a picture of this octopus on a tree crawling, and so the kids are, it's moving, it's real, look, it's real. So, again, I just kind of like using this one to show them that not everything's just true.
Well, then what about the website?
Right.
What about the website that's banned dihydrogen monoxide?
Yeah, we talk about that. I tell them that's the most dangerous substance for in your class. How it's found in every cancerous tumor. It's the number one ingredient in every pesticide. And they're like, why are we using it? So, just, I guess, remember they're nice and embrace it. Cool.
Anybody else?
I don't think it's on.
That's still on. Oh, that I don't know.
Yeah. Anybody else have anything? Sure. Yes.
Mermaid. Yeah.
They exist. They're real.
Jeff wants this
I
one.
can actually tackle that one because my next door neighbor told me that there were mermaids, and she saw this awesome show on Discovery Channel. So she ended up taping it, and I watched it with her. And within the first 5 minutes, everybody that came out with their little name and their institution, I Googled them, and they were all actors. So if your students are telling you the same thing, tell them to Google the names, and they're all actors.
And on the History Channel, all the alien ones.
On the History Channel, it's all about Nazis.
Oh, yeah, they are. Yeah. I used to be one. Yeah.
Common we get with our students is that gravity always pulls down.
Instead of in. Yeah.
Because of what they observe, they think we're all going down.
Down on Earth.
Yeah, it's like you have this notion when you're 4 years old, and then someone shows you a globe, and it's like, oh, I gotta throw that idea away.
They're like, oh, so you're upside down?
Yeah, why don't you fall off?
Or there's no gravity on the moon.
Yes, they think they'll just float away.
And the reason that the astronauts were able to stay on the moon was
Yes,
that they
magnetic
had
boots.
boots.
So funny.
True story. Mass versus weight is always a
Yeah.
All right, what else? I'm sure there's tons of experience.
It's hotter when you get to the top of a mountain because you're closer to the sun. No, that's okay. I just get that a lot.
Where the up and, north is up and south is down. Like, yeah.
Thank you guys.
Guys, thank you so much. It's really interesting. We kind of forget what people leave high school and then college and then the rest of the world. And they have these weirdest beliefs. In fact, there was a, I don't know if you guys have ever seen John Oliver. He's a comedian, kind of like The Daily Show over on HBO. And regardless of your political affiliations, he did something on the Republican National Convention. And what was fascinating was he made an argument that people's feelings eventually became the facts in their mind. So if you feel it, then it is enough to be a fact. What's scary is he showed more than one politician saying, because I feel it, it's now a fact. And that is scary. And ironically, I had a conversation with my pastor 2 weeks ago. And his conversation with the pastors around San Diego, they were saying, something that we're really challenged with today is people regard their feelings as what's true. People regard what they think, and it's a really scary time when you deny all the facts, the science, and the literature, and you go back and think, because I feel this way, it must be true. So this is very relevant, because not only are we having misconceptions with these ideas, we're having misconceptions that science is actually a real thing. And that's a challenge that we have in today's world. So I'm going to leave you with this. Where do we go from here? And there's going to be a few things that we're going to do, but don't worry, we'll get you out in more than enough time. So, wow, is that too small? Let me make sure this is a little bit bigger. Let me find out how to make it bigger.
Change the color.
Change the color? I will try. There it is. 14. Let me make this to 18. That's kind of better. Let me turn this to 18 down here. It's probably easier with two hands. Sorry, this is going crazy. Okay, that works. It doesn't look pretty, but it works. So where do we go from here? You know, this grant is all STEAM, so I'm going to ask you a few questions. How can you incorporate more STEM activities in your classroom? But the fascinating thing that I got from this, from the workshop over at the Fleet, is you cannot go so STEAM and STEM and engineering and forget some of those labs that really give students that firm understanding of what works. You have to have a balance of what works and what can you do to be creative. And it cannot be all the way one or the other, because if you go all the way one or the other, then you get a little bit of frustration if you go a little too open, and a little less learning, because they'll do something that's really cool, but they have no idea what it means. So where do we have to go? Like, how can we plan lessons? Number two, how can you incorporate either 3D printing or coding in your classroom? I did not look at the survey results. I know I'm bad. I'll find out the survey results soon. But whatever the survey results are, I'll share with you, and we'll make sure that we incorporate that for these January 5th and 6th. And how can you share your experiences with other teachers? I'm going to really stress this. If this ends here, then we have failed. This is a third of the science teachers in the district. And the point of doing these activities this year is to really share ideas with others, kind of share these lesson plans and these lesson units to people in the district so that people could use them, and also encourage our administrators, like myself, ironically, to buy these equipments so we could really bring science forward, okay? And so there is a tiny URL with workshop feedback. It's called tinyurl.com/SUHSD workshop feedback. Two things. Please rate today. Today is the 30th. If you did not do this for yesterday's workshop day, could you also do that one? And then before we go any further, while you guys are starting looking into that, I'm going to invite Miss Melanie up here. Because our eyes are always watching. And as we watch, we always make sure that we identify some people who have gone a little bit above and beyond. So I'm going to give this to Melanie.
All right, so remember, if you see someone that you think, I already had 2 names brought to me from today. You see someone, again, going above and beyond, please let me know. Please let Tony know. Because we want to reach out to you guys. Now, this, unlike the Oscars, you can only get one, okay? So if you already got one, still behave, okay, Lauren? Okay, but you only get one. So there are two folks, two of them already have them, but there are two folks that were just presenting up here today that did a wonderful job. So I'd like to recognize Dr. Dave Hecht and Dr. Jeff Veal. And Ken and Sharon already got one, but we can clap for them too. Thank you guys so much. Thank you. Speech.
I have a bright idea.
Speech.
Thank you very much.
Uncle Fester?
Yeah.
Thank you guys so much for all that you've done. Thank you. All right. Now, sadly, I know I didn't tell these people. This person's not. There are two people that are winning awards that are not here today. But we'll announce. I know. Ooh, must be present to win. Okay, I'll go ahead and announce them because one of them has been carried over since the summer, and I feel really bad. But this person isn't here, but she will get hers. I'll either take it to her or we'll just announce it again. But we'll have to wait till January. So, and Joan, you can tell her. It's Miss Susan, too. One of our 7th grade science teachers. She came up. She's gone above and beyond for the group. She came up and helped Shannon present last time, and she's done a really, really great job here. So that's for Susan. Sorry, she's not here. Now, this one, she's not here either. And she's going to be really mad because I just went to lunch with her and I didn't even tell her. This is for Shannon for many reasons because Shannon helped me with Canvas. Shannon presented yesterday. She's in a lot for GS1. So this is for Shannon, but we'll give it to her next time. So maybe we don't tell her. We don't tell them. Surprise them. Okay. This next one is for someone who's quiet, but this person is always paying attention. This person is always here on time, always super helpful, and is just so happy to be here. Always has a smile on his face. Asperto. He's the most reliable person I know. There you go. Thank you. Okay. This next person did a great job and was recommended by 3 people last time. Oh, he did a great presentation, his project last time, and he had this great project with water striders, and he's got some awesome hair as well. Ryan! Where's Ryan? Ryan's not here either? Where is Ryan? I just saw him.
We will take it back.
Is he in the bathroom? Everybody's in the bathroom. Oh dear. Okay.
Well, also, I just texted him, but if he gets here in time, Jonathan Bion, he is the tech person for San Isidro High School, and oh my goodness, did he go above and beyond? The district with the new firewall is ridiculous, and they are not letting any outside computers or personal computers get logged on at all, unless somebody physically goes in there and adds a certificate for each and every person. And he has just been an amazing, amazing partner. So if he does stumble in here, and I'm knocking or walking here, just give him a big clap because I'm going to email his, the principal. He's just been amazing.
Yeah, I'm going to call. I said, who's your boss? And he was like, he all panicked. And he told me, and I said, I'm calling her because she did such a great job. So I need to give her a call before we leave. And we'll let Hector know too. But yeah, that was really nice. We have so many people that are behind the scenes too that we want to thank. And Hugo, we thank Hugo for his videotaping services. He's behind the scenes helping us. And the assistant principals here at San Isidro and the principal, Mr. Espinoza, for helping us organize. This school has been so nice to have us here. It's very nice. It's air conditioned. Some of you have asked us, again, why do we have it here? Well, I love Castle Park. I really do. But do we want to sit in the cafeteria at Castle Park with no air conditioning today? Probably no, probably not. I love Castle Park, you know I do. That's my home school. But it's hot. It's kind of hot outside. So we want to make sure everybody's comfortable, and hopefully someday we'll all have air conditioning. Okay. So again, a reminder, if anyone is going to CSTA, please let me know, because we do need some people to volunteer to sit in the booth to do some recruiting for some new science teachers this year, okay? Or if you have any colleagues that are going, please have them contact me. Is that it?
I think, and here's the last thing. So the survey results are up. So
this is not a guarantee. I'm going to put that out there. We're going to do our best. But it seems like right now, option 1 was the winner, just by a nose, with having a first day field trip, and then the second day really being a time to do some maybe 3D printing, and also they'll spend the last part of the day doing some curricular work. So that's kind of what we're going to look at. So I'm going to be working with some of our partners to see if we can get that, because it's very valuable to go out and work with other people. If I don't get that exactly lined up that way, please forgive me, but I will try my best to get it that way. I think last thing for me, I'm a skeptic as much as I'm a positive person. When I was going into all the classrooms right before, I was kind of nervous. I was like, what am I going to see in these classrooms? Is it even going to work out? I was floored. I was really, really impressed to see how many different activities were being created by all of you guys here. It really put a smile on my face, and it really made me excited for what is already happening. So I'm going to put the floor. Does anybody want to say anything else? Yes.
If anyone's interested, we're going to go down to C180 for happy hour after. If anyone would like to join us. Right down the beach, right down Palm, on the beach.
And they have great
ID.
calamari.
And Brussels sprouts.
Brussels sprouts. Anybody else? Anybody? Go once, twice?
So guys, I want to make sure that you guys leave early. Again, please do not take any equipment unless you documented it in the Google spreadsheet that you are the person taking that equipment. If you have not done that yet, please make sure you double check. So get with your teams. Also for the observations times, make sure you guys do that. Anything that is left here, I'm bringing back to the district. Yes?
I don't know if this is, but all of step in biology is signed out to people, but I noticed there's boxes over there. So I don't know. But everything's
That's only the vernier equipment. So the vernier equipment.
Okay, but somebody says assigned it, so that person did.
Okay. Anything else? So last but not least, round of applause. Thank you guys so much. Please help clean up, and we are good to go.